After the June 12, 2025 Air India AI171 accident, a preliminary accident report was published by the Government of India's Ministry of Civil Aviation, Aircraft Accident Investigation Bureau, the AAIB. It was distributed a month after the accident on July 12, 2025. The preliminary report provided some ambiguous information that should have been better clarified. However, the inept media and self-described aviation experts, ghouls, one and all, couldn't wait to distort the only evidence made available, evidence that should have been better reviewed before publication. The inept media and self-described aviation experts, also known as the ghouls, sensationalizing of the accident led to a public appeal by AAIB Director General GVG Yugandhar for respect for all affected by the accident. It was published 5 days later on July 17, 2025. Yugandhar called for the public to wait for the complete report and then promised AAIB updates. Yes, I did use the term ghouls to describe the inept media and self-described aviation experts. A ghoul is a creature from folklore, but it describes one who takes pleasure in sensationalism and has an interest in the macabre. They don't think about what they say to stir up emotion. They just make assumptions when the camera light comes on. The ghoul's credo is, no facts required. The ghouls had changed the investigation from the start. They made character assassination attacks a part of the Air India 171 investigation even before facts could start rolling in. Hello, I'm Stephen Carbone, and this is By Reason of Air Safety. I take aviation safety very seriously. I've committed a 40-plus year career to it. I've made many mistakes, I'll humbly admit that, but my focus has always been on improving safety and aviation in general. What I really find detestable is defamation of pilots, technicians, flight attendants, air traffic controllers, and all aviation professionals, especially when smears are against the deceased, people who did their best to save lives. But to slander professionals just to sell one's personal brand or a media personality's name is the lowest of the lows. Now consider this statement on page 14 of the AAIB's preliminary report. In the cockpit voice recording, one of the pilots is heard asking the other why he cut off the engines. The other pilot responded that he did not do so. It's a simple account, though poorly written. Yet there's no talk of sabotage, no argument, no fight for control. But let's see how the ghouls in the media and the self-described experts interpreted this ambiguous information. Somehow the ghouls in the inept media and their self-described aviation experts created words like suicide and deliberately crashed from ambiguity. They then reported these fabrications as truth. They smeared two professional pilots without any proof to support what they reported. The ghouls said fuel shut-off levers could not be unintentionally unlocked and moved, or calling the concept of moving the fuel shut-off levers as a horrific theory. Then more headlines with alarming questions or the ever-ridiculous, shocking claim. This isn't the reporting of factual information. This is speculation wrapped in sensationalism. The media, both written and televised, tried to sell a fairy tale instead of facts. These so-called aviation experts and compliant media have no integrity. To sell news, they tried to destroy the accident pilots' reputations and launched an unprovoked war on their families. Now, the concept that an Air India 171 pilot shut down the engine should never have been made public. Not at that sensitive point in time. Why? Because of context. Looking at the cavalier way this was documented in the preliminary report, it's impossible to determine how the statements were made. Were the pilots screaming at each other? What was the level of energy? Were both pilots baffled at what was happening? That information should have been held back for some later post-investigation point in time. There's a difference between reporting want-to-know information and reporting facts. Instead, the ghouls, especially the uninformed media, and is there any other type, jumped on the ambiguity. And when the AAIB reported the engine shutdown in this way, it proved to be a large mistake, the first of three. A second mistake was giving credibility to the ghouls' headlines. I believe the Indian Supreme Court and Air India's management had the best intentions. They defended the integrity of those doomed pilots. However, with all due respect, the Supreme Court and the Air India CEO should have stayed out of it. Once they acknowledged the ghouls' headlines, they provided those headlines a modicum of believability. George Bernard Shaw once said, "Never wrestle with pigs. You both get dirty and the pig likes it." A third mistake was when the Indian Pilots Association, the IPA, defended the pilots. Again, their defense was understandable. It was noble. However, the IPA supporters heaped more credibility on the ghouls' smears while extending the ghoul narrative's public exposure. Sometimes silence speaks loudest. In addition, emotions will never win arguments against those who act like children or ghouls. What should be asked is this: did the cockpit voice recorder, the CVR, pick up the original movement of the fuel cutoff levers? Would the CVR pick up the movement of the fuel cutoff levers and tell us if the fuel cutoff levers were actually moved? And would the CVR pick up the click of the switches being locked into position? The flight data recorder, the FDR, would pick up the transition from run to cutoff, but it would track the fuel cutoff lever's movement. Or should I say, would it track the fuel cutoff lever's movement, or would it only sense the actual changeover from run to cutoff? I believe the fuel cutoff levers were never originally moved by either pilot, and neither pilot cut off the engine fuel. But with no available evidence, the AAIB enabled the ghouls to create a narrative that was hard to unprove by the untrained and inexperienced. Now, whether the fuel cutoff levers were actually moved is the monumental task facing the AAIB now that the public was convinced to believe otherwise. In this podcast episode, I aim to demonstrate how the fuel was cut off, but it requires some setup, so please bear with me. But first, let me tell you a story. In 1993, I was working on a 727 trailing edge flap rig with a rigging genius named Dan. The aircraft, the 727-100, had been grounded for over a week. The inboard flaps and the outboard flaps would not extend symmetrically. What I mean is, they were not extending in line with each other. Even though they were independent systems, they had to be symmetrical. You see, the 727's trailing edge flaps interact with outboard ailerons and leading edge Kruger flaps and slat systems to ensure they operated correctly during each phase of flight. To put it simply, if flaps were out of symmetry, the plane couldn't fly level. It was that important. The flap system had numerous cables and push rods, quadrants, and belt cranks, a real confusing series of mechanical chaos. However, when Dan had finished troubleshooting and fixing the flap system, he found the culprit was a dog-bone-shaped rod about 3 inches long with a rusty bearing, like in the top right corner of the picture. The small rod, which ensured both the inboard and outboard flaps were in step with each other, was causing erratic inputs because the bearing was alternately seizing during the operation. It was a hidden failure, one that wasn't expected but made blaring sense. That one small piece, the smallest in the flap system, threw off systems all over the airplane. I'm telling this story because others who tried to fix that 727 trailing edge flap system concentrated on the obvious: the transmissions, flap track roller bearings, jack screws, and hydraulic components. But Dan focused on the logical problem: the small dog bone shaped rod with a bad bearing. It's like obsessing on the confusing words between the two Air India pilots without context. Air India Flight AI171, a Boeing B787-8, registration Victor Tango Alpha November Baker, crashed on June 12, 2025 in Ahmedabad, India, while taking off at a Sardar Vallabhbhai Patel International Airport. Both engines lost power, thrust was gone. The aircraft impacted on buildings just beyond the airfield. The accident investigation is being conducted in accordance with Annex 13 of the Convention on International Civil Aviation Organization, the ICAO rules. No sooner had the burning accident site's fire been extinguished than the parade of ghouls launched into speculation mode. In aviation, the term aviation expert is met with enormous skepticism from those of us calling ourselves aviation professionals. However, these so-called aviation experts were destroying the reputations of the deceased, and that's why they are aviation ghouls. These aviation know-nothings went for the big stuff without thinking logically. From the preliminary report statement, how did the ghouls make the leap to say one pilot shut down both engines? They assumed with 100% certainty that one of the pilots had to intentionally move the fuel cutoff levers from run to cutoff. Why? Because the ghouls surmised there's no way the two cutoff levers move themselves. But what if the cutoff levers didn't move? The flight data recorder, the FDR, said they did move. Or did the FDR just sense the levers transferred power from run to cutoff? One pilot asked if the other moved the levers to cutoff. The other pilot said he didn't. To be honest, suicide wouldn't make sense, even if it was possible in this situation. Let's look at two successful suicide plane crashes, such as Egypt Air 990 and Germanwings 9525. In both tragedies, the suicide pilots had two distinct advantages: altitude and control. With Egypt Air 990, the captain was out of the cockpit when the suicide pilot set the throttles to idle, which sent the aircraft into a dive. When the captain tried to fight for control after he returned, the first officer shut off the engines, all captured on the recorders: altitude and control. With Germanwings 9525, the captain stepped out to the bathroom. The suicide pilot then locked the captain out and sent the plane into a slow descent to impact, all captured on the recorders: altitude and control. With Air India 171, there was no guarantee of fatality. Just like British Airways Flight 38, the plane could have been survivable if the descent path was clear. The altitude didn't guarantee success for a suicide flight, and neither pilot had control over the other. Second, there wasn't a struggle in the cockpit. Otherwise, the CVR microphones would have picked it up. The levers were found in the run position. So it would be sensible to ask, why would a suicide pilot who would have been committed let the plane be saved? None of what the ghouls put forth made logical sense. In factual reality, the accident pilots did act in line with their training, while the ghouls acted in gross violation of ethical reporting. Let us hope that we can now recognize that neither of the pilots even tried to commit suicide and focus on the facts of the accident. Unfortunately for defenders of the two accident pilots, including anyone investigating this accident, they probably won't catch what happened. It's likely they lack the experience and knowledge to understand what really occurred here. They are focused on the obvious, the big things, and not the logical. I'm confident the root cause is straightforward. It suggests airlines that operate this aircraft don't think outside the box. They don't know history or have the discipline to transition to an airliner this advanced while respecting quirks from aviation's past. Now, I'm forced to take some liberties with the evidence I will present. Since I haven't been trained on the 787, I have to use training methods from my past and at my disposal in order to set the stage that presents an analysis that's believable and qualifying. I must demonstrate what fuel cutoff levers look like and how they operated before the day of the 787. Please stay with me, it's important. Now, since the 787 didn't exist in the days of analog controls, pre-1990s, I'm going to use a parallel analog aircraft, the DC-10. The DC-10 had analog technology. Granted, it has 3 engines compared to the 787's 2, but I'm speaking to general airliner knowledge. If the 787 had an earlier analog version, the technology used would be close to the DC-10, similar enough to make my point. And hopefully this will help us understand the evolution of fuel cutoff levers on airliners. Looking at the fuel cutoff levers from the DC-10 pedestal, the 3 fuel cutoff levers slide up into the on position, also known as the run position, to start and run the engine. The lever then slid down into the off position, also known as the cutoff position, for engine shutdown. In both on and off, the fuel levers are locked mechanically into position. This is shown by the picture by the green circle over the lock button. You would suppress this button with your thumb and release it to lock it in position. There never was any question the lever was locked or unlocked. It had positive locking. It's important to note, for the engine fuel to be cut off, the lever has to be physically slid down about 3 inches of travel. These mechanical linkages differ from the digital technologies, as we will see in a few minutes. This picture shows the mechanical linkages behind the pedestal, in other words, within the pedestal itself, just below where the pilots are in the cockpit. Each fuel shutoff lever linkage is connected to the next mechanical linkage down the line. They are physically connected to the fuel control on the engine by some sort of tangible hardware, such as cables, bell cranks, and quadrants. And because these are mechanical linkages, there's no hidden injury. All damage is seen from above and below. Unless someone goes under the floor and takes a hammer to the linkages, they cannot be damaged extensively by everyday wear and tear abuse in the cockpit. The fuel shutoff levers on the pedestal are in orange. Blue is used for cables, quadrants, linkages, bell cranks, and pulleys that physically connect the fuel shutoff lever to the fuel control on the engine. There's no ambiguity or hidden damage. Everything is straightforward and touchable. You can feel the grease, the cold metal, and the easy movements. So why was the system changed? For one, the ease of replacement. The system from the fuel cutoff levers to the engine was one continuous electromechanical connection. Each cable-driven fuel cutoff lever system took hours or days to replace or work on. To replace any component requires breaking into the physical system and replacing the damaged part by going through the length of the aircraft fuselage. When I told the story about the dog bone-shaped rod, this is where you'd find such a component in these types of linkages. The length of the airliner plus the amount of equipment furnishings, such as seats and carpeting, wing and pylon panels, meant many man-hours and tooling to replace even one fuel shutoff lever system. The replacement and post-maintenance checks required long hours of downtime and multiple maintenance crews. This could not be accomplished on the flight line in the field, which meant more expense as support technicians were flown to the airliner being worked. The second reason was for weight. Each fuel shutoff lever assembly had a considerable amount of weight to it. The weight removed meant savings in fuel, times 2 both engines, for two engines, and for both systems. That's 2 times the amount of weight saved. Were there advantages to the analog cable-driven system? Well, yes. The cable-driven system was more robust, as I spoke about before. It could take that punishment, from hard landings to spilled fluids to dropping a large object onto the levers. The fuel cutoff lever system was like a Timex watch. It could take a licking and keep on ticking. Any punishment didn't cause unseen damage to the levers. Their integrity is visible. Any damage is visibly noticeable. They're strong. The trouble is, the transition to digital technology created consequences not foreseen, and I would add, not seen yet. In the late 1980s, there was a transition to digital fuel shutoff levers, the dawn of the two-person cockpit on all airliners, winglets, and composite flight controls, all designed to improve airliner performance, including reduced weight for better fuel economy. Digital fuel cutoff levers, like the MD-11, which was the newer and improved version of the DC-10, replaced the old systems. The digital technology has a replaceable pedestal called the Thrust Control Module, the TCM. There weren't push rods, cables, quadrants, or belt cranks that extended out from the TCM. There were mechanical workings inside the TCM, but not outside. And since the workable parts of the fuel cutoff levers are inside the TCM, no one sees any damage, if any, that the TCM incurred. There is nothing behind each fuel cutoff lever but circuitry, microcircuitry. These circuits are fragile. The current is measured not in amperes but in microamperes. A static charge from someone's clothing could even damage the circuit. And to be clear, if a TCM is damaged, it may operate normally under operating conditions for numerous flights and ops checks, but then fail without warning, like short-circuiting in 2 or more places that are indistinguishable, like between 2 787 fuel cutoff levers that could bridge the circuits from run to cutoff. No one can see the hidden physical damage in the digital circuitry. Not the pilot, not the mechanic. No one can see or tell if the short exists until it is too late. The TCM is an independent line replaceable unit. It's fundamentally a switch, like many digital system components found in your late model car. It is, quite frankly, a plug-in. How many times have digital components in your late model cars failed without warning? Are there advantages to digital technology? Absolutely. The fuel cutoff levers on the TCM can be replaced while the airliner is waiting for its next flight during a short layover on the flight line. The whole unit, after loosening 4 to 6 lock bolts with a slotted screwdriver, slides out on a track, and the new one slides right back in. It takes 20 minutes to replace, on the line with a 10-minute engine run operational check. No equipment is removed, no furnishings such as seats and carpeting, wing and pylon panels pulled out, no multiple man hours and tooling, no long hours of downtime, no multiple maintenance crews, just 2 technicians. No expense for support technicians who need to be flown to the field, and no time changes for cables or worn bearings. And because the system is completely electronic, there's only wiring between the fuel cutoff levers to the central interrogating and digital control computer. From this computer, more wiring to the engine's fuel control, like the Full Authority Digital Engine Controller, the FADEC, which monitors and controls all engine controls like the fuel control. And by removing these components, the manufacturer reduced enormous amounts of weight from cables, quadrants, etc. And this would be the greatest thing in the world, except for 2 consequences the manufacturer couldn't improve on. One was bad habits from old culture, and 2 was troubleshooting. There are many troubling things about digital technology. Many love it, but I find it enormously problematic. Rugged wiring, which is resistant to daily damage, has been replaced with digital circuits. I use the word replaced. The correct phrase for wiring that took up all major systems would be reduced or diminished. Rugged wiring is still there, just not as much. This type of digital circuitry isn't new, but compared to analog aircraft, digital circuitry is used extensively throughout the aircraft. How strong are these circuits to blunt force or extreme vibration? Please remember, circuits of today aren't wire bundles that flex and make 90-degree turns in a curve. They aren't strapped together stronger because of the bundle's combined strength. Wiring ran for the length of football fields from cannon plug to connector through grommets and in and out of pressurized and unpressurized areas. They were heavy, bulky, incredibly sturdy. Where aviation went wrong was treating digital circuitry as if it was wiring, abusing digital circuitry as if it could take the punishment of wiring bundles. Industry has done this for so long, they have absolutely no idea how and why digital circuitry fails. Industry is still convinced digital circuitry is as robust as wiring. But imagine dropping an object as heavy or a blunt as a hammer on your cell phone. Do you think the circuitry in your cell phone could withstand the shock of such damage? How about dropping your widescreen LED TV? How strong would that circuitry be to physical abuse? And consider what happens when you drop piping hot coffee or ice water on your cell phone. If you did this once a day, once a week, or twice a week, do you think your cell phone would sustain damage to its circuits? What investigators who have never worked in the airlines or the manufacturer don't understand is the airline culture. Technicians do drop 4 D-cell battery mag lights in the cockpit, perhaps on the fuel cutoff lever, from a height of a foot or more. Or how about dropping an overhead panel off the overhead onto the fuel cutoff levers? Or how about using the pedestal for libraries for such things as operations manuals, minimum equipment lists, troubleshooting guides, maintenance procedures for changing out the windscreen, tool bags, test equipment? Consider how much shock those fuel cutoff levers' digital circuits sustain during each landing. Or if the pilot's knee bangs into it from the side. Each time the pilot slaps down on the throttles. Would you see the physical damage on the fuel cutoff lever? Probably not. However, the damage isn't to the fuel cutoff lever itself, but to the microcircuit inside the lever. 1 or 2 short circuits could be made without any evidence to see. No one would know. Digital fuel cutoff levers are rigid in their mounts, and there isn't much tolerance for side strikes or damage from above if something falls on them. They aren't designed to sustain shock from falling objects or hard landings. And how much damage could steaming hot coffee, salad dressing, fruit juice, or cold water introduce to a digital circuitry? What? You think the pedestal isn't used as a table? What, you think water or coffee doesn't get spilled on digital equipment like the VHF radios? When these things happen, whether a pilot does it or a technician does it, don't you think the digital switches get damaged? How much foreign object damage can these digital circuits take, and how resistant are they to extreme temperatures, spills, or condensation? These are bad habits pilots and technicians have passed down through the decades, using the pedestal as a table or resting place, and they've been around since the pre-jet days. Many technicians and pilots unintentionally abuse equipment. They are bad habits. And old habits die hard. Analog systems like the DC-10 fuel cutoff levers were more rugged, more punishment resistant. Maybe what the latest airliners need are a few more cup holders or tray tables for the pilots. In 1993, my airline had a number of fuel harness problems on the 727. The harnesses, which were the nerve center of the fuel quantity system, demonstrated different problems on different airplanes, such as unstable readings of high or low tank quantity. Maintenance support didn't want to waste time finding the causes, so the fuel harnesses were ordered to be replaced on the spot. Trouble with this way of thinking is if you don't troubleshoot the problem, determine the problem, you don't learn anything about the problem. Some might say, with the fragility of the microcircuitry, how come we haven't seen a dual engine shutdown before? Good question. I would suggest we've seen similar problems in different systems hundreds of times a year in different airliners in hundreds of international airlines. It's just the communication is not there. I'd further suggest we'll see many more safety events like Air India 171 if we don't learn. Why? The answer is simple. Aircraft have become so technologically advanced, we don't troubleshoot problems anymore. Technicians, just like pilots, have become the airplane computer's servants. Technicians today do less troubleshooting. Technicians only replace components the airplane's onboard computer tells them to replace. Consider this. Unless the airplane's onboard computer directs the technician to replace, say, the fuel cutoff levers, those levers will never be replaced. Technicians aren't even familiar with a failing fuel cutoff lever that's about to fail. What technicians have lost is tribal knowledge. They've lost forever the lessons on how to understand the problems that can come up. Because of this move to technical complacency, technicians are becoming automatons that do what they're told to do by a computer. Another reality people don't consider is, why don't failures such as fuel cutoff levers ever rise to be noticed? Let's take the MD-11 TCM again, for example. If the TCM is giving a fault, the aircraft onboard computer informs the pilot or technician the TCM needs replacing. All the pilot and technician know is the TCM will fail. They will never know how or why the circuits or workings are damaged. According to the technology, they don't need to know. In the case of the TCM subcomponents, like the fuel cutoff levers, the levers will be replaced and the part returned as serviceable. No troubleshooting, no reason, no one cares. The broken TCM component is replaced without any further notice. The overhauled TCM is installed on the next airliner with the same part number. There will be no history, no tracking, no understanding of why the fuel cutoff levers failed. And this will be repeated all through the international airline industry with nobody knowing why, ever. This is the most safety-destructive pattern, decades in the making. Technology hasn't just made aircraft more fuel efficient. Technology is also eliminating the pilot and the technician workforces. Ask yourself, why the push for single pilot? Or why the push to make it so that the aircraft technician workforce is no longer a trade? Technology. Once both workforces are gone, they can never be replaced. In 1991, an avionics technician I worked with required anyone going into the electronics bay of a digital airliner to have on their wrist a static discharger. When one is removing a line replaceable unit, what we call a box in the electronic bay, the discharge band collected all static from walking across the hangar and the electronics bay and put it to ground by clipping on to the ground of the shelf. It neutralized it. The circuits were susceptible to static, and they were damaged by the microamps. The digital circuitry's true fragility is in its structural weaknesses. The fuel cutoff levers themselves could be damaged by static discharge or blunt strike to the levers, but not display any physical or obvious damage. The damage would be invisible. Saving money isn't limited to weight reduction. Not replacing components that could have been damaged also saves money. But digital circuitry does have a life-limited usefulness. The question is, has anyone studied life-limited parts such as fuel cutoff levers, and digital technologies. Hopefully, the AAIB has avionics people on board the investigation, and it is also hoped the fuel cutoff levers from the accident aircraft are intact for study. Specialists in digital circuitry should study the accident aircraft's fuel cutoff levers and be able to find shorts across electrical paths if they exist, or cracks in the circuit that allowed current to cross. That is where I would look. Until next time, I'm Stephen Carbone reminding you to tab. Think safe, act safe, be safe. God bless.